All right, good morning. If you are with us here live today, apologies for a little delay as we get back into the swing of things here with our online programming. If you're new to this, my name is Scott Harris. I am a planetary geologist and also um, assisting with a group in Charleston, South Carolina to create a brand new planetarium in that very historic city. Myself, I'm in the Atlanta area, and I am going to be leading you, as I have many times over the past few years, through a tour of the solar system this morning. And this will be out there for you the rest of the day and for, well, pretty much for as long as the internet is around for you to enjoy. And if you have any questions, you're welcome to ask those in the comments section of our Facebook Live feature or continue to put those into the comments at any time in the future, and I'll do my best to answer them. But we're starting something special here to kind of get back in the, kind of kick off our online programming after a bit of a hiatus. And we're using this incredible upcoming total eclipse to do that. And we're going to actually take a journey from the southeastern Atlantic coast here all the way to the midline of Totality, hoping for good weather coming up on Monday, April 8th in the early afternoon out in the central part of our nation. We could be anywhere from Texas to the Midwest. Right now, I'm sort of hoping that some areas in central Texas will actually start to look good in the forecast, as much of the U.S. right now looks like there's going to be significant cloud cover, but that's kind of the way the eclipses go. But along the way, we're going to look at some other things that have to do with both Earth and space, and that's the subject of my research, which is asteroid impacts and comets as well. Things that create violent explosions with our planet and others. And we'll take a look at some of the scars of those here as we go across to Totality. This morning, though, we're going to take our tour of the solar system, but as always, we're also going to look at our night sky. And to do that, we're going to go out now over to our Stellarium program and look at the evening as it would be after sunset if you're in a clear sky area tonight. As you look off into the setting sun, you can catch Jupiter there bright above the horizon. Coming a little higher into the sky, we see the bright red star Aldebaran, the eye of Taurus the Bull, and next door, we're still holding on to our winter constellations here with the very famous Orion the Hunter, noted by the 3 stars of his belt and the bright stars of his shoulders and kneecaps, including the very, very large red supergiant Betelgeuse and the blue giant here burning much, much hotter than the reddish Betelgeuse. This is the star Rigel. And across to the south here, to the southeast, we find the brightest star in the nighttime sky, and that is the dog star Sirius, the eye or the nose of Canis Major, the big dog. If you have a hard time seeing a bull and a hunter and a dog, that's why we have planetarium software, when we have planetariums, and we can immediately fill in the pictures here to give you an idea of what the ancient Greek and Roman astronomers noted in the heavens. And we can also draw in the lines there as guides, taking the art away. This is how often you see star charts and maps. As we zoom out and look around to the other side of the sky, we will see Hydra, the sea serpent, rising from the southeast, and Leo the lion. Don't believe me? There we go. And around to the north, we see Ursa Major, the big bear, and more noted is his back and tail, which we call the Big Dipper, what we call an asterism, a star shape, as opposed to those 88 constellations that draw out those pictures in the sky. We're going to advance in time here all the way to, we're going to go very fast, very, very fast, until we get to early next week here we have April the 8th at just around noon. This is set for, the time here is set for Eastern time. The place I'll be viewing from will be in Central time though. So we're looking at a little after 1:30, around 1:30 or so Central time. So we need to advance this here to about 2:30 or so. And you'll notice we just went dark. Just a flash there. And if we zoom in here on our sun, we will see a simulation of the corona that you would expect to see during totality. In the Carolinas, Georgia, in the southeast here, you'll only get about an 80% partial eclipse. You won't get this incredible totality that everyone is going out to the mid parts of the country to see, or up into New England. But for about 2 to 4 minutes, depending on exactly where you are in that path, the moon covers the disk of the sun, giving that incredible opportunity to see the bright corona around the edges. You might also notice that during totality, you'll have an opportunity to see Venus and Jupiter. And if you pan out, you may even see Saturn and Mars. And there is a chance still of a comet out there that may make a sort of photobombing appearance as things get dark. And so I'm going to come back here just for a moment. We're going to hop back here, and now we're going to go in a different direction. Rather than view from the surface of our planet, we're going to go out into space with the help of our open space program. And I thought this morning we would go first to our the star of our show. Well, the star of our show on next Monday, the literal star, is our sun. But right after that, I guess, guest starring in the antagonist role for the day is our nearest planetary neighbor, our own moon, Luna, as we call it. And we'll take a look at it. And these are in real-time shadings. So the moon on next April the 8th will be totally new. During an eclipse, by definition, the moon is a new moon. And this is the side that we would see there. That's the near side of the moon, totally in shadow, which means that on the other side, we see the far side of the moon. That's the part that is illuminated when the moon is new. And we will be looking at our near side here completely in shadow. We're not quite there yet. We're getting very, very close. And everything will be in alignment during the early afternoon of Monday of next week. And while we're here, let's go ahead and take a quick look at our own Earth. And we'll be back to Earth here in just a moment, but just to show you that it is out there. And again, if we sort of change our view and look back there in the direction of the sun, we can look around for where our moon is right now. Let's get kind of an overhead view here of the Earth-Moon system. And we see our moon here, the Earth here. And now let's look for the sun. And we notice that the moon has to travel a long way relative to its orbit around Earth in these next few days. And it does. It's flying along very fast, as we are careening around the sun ourselves. And the moon and Earth, the sun, will be in perfect alignment coming up on next Monday. Let's go ahead and take a look in at the closest planet to our sun. And we'll do that here. Let's see if we can. We're getting a little lag in our program. If that does that, again, we're just trying to get things back up here after our break. So if we end up having a few hiccups, I apologize. And let's see if we can maybe just having a little bit of a software issue here. This is trying to pull a great deal of data, and that came back to me. So I'm actually going to go ahead and call our open space program back up here. It takes just a minute to reload things, and we'll get that back up. While we're doing that, I'm actually going to go over. If you see me looking away, I'm often monitoring anybody who's with me live, and I'm going to go over to our site here. We're going to have for the next few days a both live and recorded programming that will be available here on our Charleston Planetarium Society Facebook page, and also my YouTube page. Much of the content will be uploaded there as well, and that is YouTube at Georgia Craters. And you can find that in the announcement for this programming on our Facebook page here, if you need that direct link. And so if you'll give me just a moment here, I'm going to over to our make sure that I am getting things back up running here. We're almost back. And let's take a look here at the head back out to space, and the first place we're going to head to is our, as I said, the closest planet to our sun, and that is Mercury. And we'll go back to that now with our open space program. And here we go. We're going to head there into Mercury. And notice the time here. When I reset the program, it changes, and so I want things to look as they really are right now, with all of the sun angles correct. And as we approach Mercury, we see a world that looks a little bit like our own moon, but actually is quite different. What they share in common is a very ancient surface, with areas going back more than 4 billion years old, heavily cratered. The craters on Mercury, we believe most of those are created by cometary impacts, as those big balls of ice careen in very close to the sun. Often Mercury is in its way on its approximately 90-day orbit around our central star. If you look closely at the ejecta from craters, many times you'll see this bright white ejecta from relatively recent impacts. When special instruments on board the Messenger mission looked at those, they actually found evidence of water contained in the minerals, or maybe glasses embedded in the ejecta. That's likely inherited, in my opinion, and the opinion of my colleagues, likely inherited from the cometary collisions, but there's a chance that some of it could be water from internal sources as well. As we allow the data to come in here, we see the details of the surface, and if you look carefully, sometimes you can see very ancient lava flows that go back almost 4 billion years old. And all of these data, again, provided by the Messenger spacecraft that was orbiting a little more than a decade ago. We have another mission that is arriving in about a year and a half at Mercury. That's called Bepi Colombo. That is being flown by our friends with the European Space Agency. The surface here on Mercury is extraordinarily hot. at around 425 degrees Celsius. But just go to the shade. As you go over across the terminator, the divide between day and night, those temperatures near the equator drop from those 425 down to minus 180. So from incredibly searing heat to unimaginable cold. As you approach the poles, things can get even colder, and in some of the areas near the poles, just like on our moon, we have evidence of ice accumulated in some of those craters. Literally some of the coldest places in the solar system, even though it's nearby to the sun, because deep in those craters never ever sees any sunlight. In contrast to the incredible cold of those craters is the surface everywhere on the next planet away from the sun, and that is what we call often our sister planet, Venus. It's our sister planet in that it is relatively close by. It's around the same size as Earth, just a little bit smaller. It has clouds, and that's about where the similarities stop. As we look at the cloud tops here, incredibly reflective, allowing us to see Venus very, very bright in our nighttime and even daytime sky. Did you know if you know exactly where to look, you don't have to have a telescope to see Venus in the daytime? But it's very hard to spot because it's often close to the sun, and you would have to know exactly where to look. If we want to see the surface of Venus, we have to peer through the clouds, and to do that, we have to use a different sort of very different type of viewing. We have to use radar to beam radar waves through the clouds and bounce them off the surface to come back to our spacecraft. And we have to get rid of those clouds. And that's what the radar does for us. It sees through them. And now we can look down at the surface features. These are data provided by the Magellan spacecraft that was active in the 1990s. And as we look there at the surface, we see some evidence of asteroid impacts. But we don't see many craters here because we believe about 500 to 600 million years ago, the entire surface of Venus was essentially kind of overturned. There's evidence of having tremendous volcanism, and in doing that, it destroyed the earlier larger craters, and so we have only the large craters that have formed in the last 500 million years that are available to us. And I'm going to try to get rid of the see if I can get rid of the atmosphere here. We want to actually call the atmosphere up, but then we want to see if we can actually take that away so we can see just a bit better. There we go. Many people like that orange color. It gives the impression of it being hot. And the Venera spacecraft that have landed on the surface have verified that indeed the sky is sort of an orangish, yellow, hazy color. The area we're looking at right now are not the basaltic flows, but instead an area that we call tessera. These are possibly comparable to the continents here on Earth, where we see faulted and folded mountain ranges. We're very anxious to get more data about these areas to see if they are in fact comparable to Earth's continents. But most of Venus's surface is characterized by basalt, just like our seafloor, or most people when they think of basalt think of like lava flows in Hawaii or Iceland. Here we see some flows that are coming out from an area of impact. Rather than a volcano, we have melting of the surface and flows of material out across the surface here. Anything that's molten on Venus's surface stays molten for a while because the surface temperature is so incredibly hot. The reason for that is that the atmosphere is filled with a thick blanket of carbon dioxide gas. That carbon dioxide acts as a greenhouse gas, is an extremely efficient greenhouse gas, particularly with the amount of carbon dioxide that you have on Venus, and it allows for temperatures to be maintained at almost 500 degrees Celsius. As we look around here, we can see areas that where we have these lava flows, lava plains. They appear dark in radar because they're relatively smooth. So now let's head on to our the next planet out away from Earth and the Moon, and that is our red planet Mars. Around Mars, we have highlighted the orbits of its two moons, Phobos and Deimos. A year ago, I would have told you that both Phobos and Deimos are captured asteroids. But now there's some evidence that little Deimos, the tinier of the two, might be composed of pieces of Mars itself that were ejected long ago by an impact. Sort of a small version of our moon. But the larger Phobos, we still believe, is a captured asteroid. And if we want to see Phobos up close, we can do that here. And let's head over and see the incredible surface sculpting of this tiny world. We see these striae along its surface that are scours from the ejecta from a large impact that occurred on this body. So it looks like a lumpy potato there in space. That's kind of how asteroids look. And now let's take a look at its parent planet, Mars. We have an armada of spacecraft around Mars that have been active, many of them for quite some time now. Of course, we have rovers on the surface. So we have incredible amounts of data to guide us around this world. We see at the poles ice caps, somewhat similar to our own. But as they shrink and swell seasonally, they leave behind these deposits here of ridges of sediment that we can analyze even from orbit to determine things about Mars's ancient climate. One of the most fascinating things about Mars is that there's evidence that because it does not have a large moon to stabilize its tilt, or what we call its obliquity, like our moon does for us. Our moon kind of is a gravitational tractor that keeps us from tilting over. We sort of go back and forth just a little bit around just around 22 to 23 degrees of tilt. Well, Mars is almost straight up and down right now, but there's evidence that in its past it can tilt over on scales of hundreds of thousands of years as much as 60 degrees. So it's almost like the equatorial or tropical areas would become polar and the poles would become tropical. It's a very different sort of a world than we experience. And if we did not have our moon stabilizing us, you can't say that life wouldn't be here, but I think life would be very different if we had to constantly adapt, if things on our planet had to constantly adapt to such incredible changes in climate over relatively short periods of geologic time. So we're looking here at a global mosaic. It gives you sort of an impression of what Mars really looks like in its true colors. Here we find the large Valles Marineris, one of the largest canyons in our solar system, stretches out as wide as the United States is from coast to coast and much deeper than our own Grand Canyon. Over here to the west, because we have south at the top right now, we see the Tharsis volcanoes. Over in the shadows, we find the largest volcano on Mars, Olympus Mons. But as we turn around here to the east, one of the things to point out is, let's actually, I can also, in our program here, I can turn the shadows off, basically, so that we can see the entire world. And when I do that, as we move around, we won't have to worry about, well, we still have to worry about the sun shading, but we don't have to have the, that. We can turn that off too, or we can change time. There we are. Okay, so looking at right now, the nighttime side of Mars. And what I want to do is we're going to come around here and pan back, because I want to show you an area here that let's actually advance time just a bit, and we'll go, actually we want to go backwards in time, and let's see, looking for a feature here on Mars that you can see from Earth, and that is this large dark area called Syrtis Major. And the reason I draw your attention to that is right next door, you'll see this sort of scalloped area, kind of a semicircle. That is the Isidis Basin. And right on the edge of the Isidis Basin is where our rover Perseverance is right now. Back a few years ago, it landed here on the edge of Isidis in a smaller crater called Jezero. And I'm going to actually go over now to a different data set. We'll see if how fast the web is working this morning. And we'll go here to our a data set from that we call a CTX, and that is also try bringing in another part of the data here, and we're going to see very, very high resolution data. Sometimes it takes a moment to come in, but as we look here at the surface, we can see a lot of detail. What we're looking for are rivers, ancient rivers, 4 billion years old. And this is a great place to look for them because Syrtis here is very old, about 4 billion years. And I always have to kind of guide on a few small craters here to find Jezero. I look for this elliptical crater here, indicating a relatively shallow entry of that asteroid to hit the surface. And now I'm going to come up from that, and you're going to see a river channel right there. And you might notice that sinuous snake-like river over here. And then there's a crater in the middle. Well, that crater, that's Jezero. And you might imagine that water came out of the hills, filled this up as a lake, and then flowed out the other side. And where that river emptied into the lake, you might expect the sediment to settle out and create a delta. And that's what many of my colleagues think happened right here to create this feature that looks a lot like what we call a bird's foot delta, like the end of the Mississippi River. And so Perseverance landed right out here and now has crawled its way up here along the edges of this delta, analyzing the sediments, collecting samples that we hope to pick up from Mars with future craft. Now, I don't dispute that this is a delta, but some of us have different ideas about what the water was like that fed this. While some people require that for their models that this be a flowing, a very big flowing river, some of us believe this might have been under ice, a glacial river, a glacial tunnel. And those can form a type of delta as well called came deltas. And perhaps that's what it is. The reason that's important is there are debates about what Mars's atmosphere was like back 4 billion years ago when this formed. And was it very, was it thick and damp and with a lot of water, or was it still pretty thin? Because if you had a big ice shell on top of everything, had a big glacier here, it doesn't require as thick an atmosphere as if you require the rainfall to occur on the surface and feed these rivers without that ice pack. So that's where Jezero is. And let's go ahead now. We're not going to hit every place this morning. I do different versions of this, and we may look at other places in other installments of our tour through the solar system. Let's head out into the outer solar system now and see our gas giants, including mighty Jupiter, the largest planet in our solar system. Around it, you'll find these moons. Jupiter and Saturn have lots of moons. I've frankly lost count at this point because astronomers continue to add smaller and smaller moons that they find. Right now, Saturn is in the lead. Jupiter is losing, but give Jupiter enough time. I'm sure it'll catch up. But 4 of the moons around Jupiter are really special because they're really planets in their own right, including Io, the most actively volcanic body in our solar system. We've imaged it now with a number of spacecraft, including most of the data that you see here from the Galileo mission. But we now have images we've taken with the Juno spacecraft. You see these just enormous shield volcanoes here. In a surface that we believe is largely basaltic but laden with a sulfurous frost. Another world where there are almost certainly volcanoes, but we can't see them, is next door on Europa. Both Io and Europa are tugged by, they're basically caught in a tug of war between the gravity of Jupiter and the gravity of their neighboring moons. And so the insides stay warm due to what we call tidal flexing, and that allows volcanoes to erupt. But where are the volcanoes here? Well, we think they're underneath an ocean. There's plenty of evidence now that Europa has a thick ocean beneath this ice shell with more water than all of Earth's oceans combined. The heat from those volcanoes allows it to stay molten. But of course, at the interface with space, it freezes solid. The Europa Clipper mission is set to launch next fall and will carry a scientific payload out here that will arrive in about 2030. And it's going to examine Europa with in more detail than we ever have before, and will also be trying to look at eruptions of watery ice from these ridges. And it's in those plumes of material that we imagine, if there's anything living in that ocean underneath, the chemical evidence of that life might be in those plumes. So we're going to figure out how to examine those plumes and other features of Europa to determine if any type of microbial life is present or ever has been present in the European environment. Let's go on out now to everybody's favorite planet. I say that because no one can resist Saturn's rings. Just like Jupiter, many moons around this include lots of moonlets, if you want to even count the particles in the rings. The rings are about 100,000 kilometers across, 50,000 on each side. Estimates are now that they have only been there for a few 100 million years. They haven't been there since the beginning of Saturn. And they are being consumed by Saturn. So given another couple 100 million years, and if they are not resupplied, they will vanish. But you see those orbits out around it. Those are the orbits of 7 of Saturn's moons that also are really small planets, including little Enceladus that has those ridges, much like we just saw on Europa. The Cassini spacecraft saw geyser-like eruptions rising above the Enceladus surface. And those eruptions were coming from cracks near the southern pole of Enceladus. You see a history of cracking there on its surface. So this is another world. We think there is liquid and liquid water underneath the ice, and maybe environments that could be conducive to some sort of microbial life. We don't know, but we know the chemical ingredients are there. And so you'll see a lot of focus in coming decades on trying to get a mission back here to examine these ices and those volcanic eruptions. In addition, we have a mission slated for going to Titan, Saturn's largest moon and the second largest natural satellite in the solar system. Both Ganymede at Jupiter and Titan are larger than Mercury. As we look at Titan, we have to deal with its atmosphere, just like we did at Venus, a thick atmosphere. In this case, not of carbon dioxide, but of nitrogen, kind of like Earth, except along with nitrogen, we have about 20% oxygen, and that's not here on Titan. This is about 96% nitrogen with several percent methane, and that methane is creating a haze there in the atmosphere that we see as that orangish color. The surface features underneath, we have to, again, analyze with radar, peering through the haze and clouds, meaning that the dark areas are smooth plains here around the equator. Imagine those as like the desert southwest of Playa Lakes, filled with rainfall, but not of water, but of methane and ethane, acetylene, hydrocarbons. And those plains then are kind of carved out. You don't see rivers here that develop from that flowing liquid, and then it evaporates and forms clouds over. Near the poles, the pressures are different and the temperatures are different, and that allows some of the methane to settle as lakes, small seas, if you will, that we believe remain liquid. But we have the mission Dragonfly headed here in just a few years, and it's going to be a quadcopter drone, big one, like the size of a car, that is going to fly from place to place to analyze the chemistry and geology of this world. I'm going to skip over Neptune and Uranus for now and head to little Pluto. Back in 2015, the New Horizons spacecraft took about 6.5 hours to fly by Pluto and its moons. We see there the outlines of their orbits, including Nix and Styx and Cerberus and But as we come in close, we notice that those moons are just little chunks of ice, but one is special, and that is Charon over here. Charon and Pluto are really a double planet system orbiting around a place that is outside of Pluto. So they sort of, if we watch this, it would sort of look like they were wobbling around each other. But we're going to take a close look first at Pluto and then end with Charon. And when we look at Pluto, we see another ice world. Frozen water ice makes most of the crust, but this large basin here called Sputnik is filled with nitrogen ice. Nitrogen ice that appears to have something convecting underneath to create these cracks in its surface. And we also have this thumbprint terrain that you'll see with these little pits and ridges. And those are from sublimation, from the nitrogen frozen here, turning immediately to gas during the warmer periods of Pluto's orbit around the sun. We see evidence of ice volcanoes here as well, what we call cryovolcanism. Icy, cold volcanoes, not the hot, red, incandescent stuff like you're used to here on Earth. This is a very dynamic world, and without the New Horizons spacecraft, we would have never known that this has such a rich geologic history, including things that look like almost like rivers, right? I mean, these are probably tectonic features, rifts that have opened up in extension, but there's evidence that methane may have flowed out of the walls of the canyons and for a brief period of time been mobile on the surface to modify these so that they have that more river-like appearance. And finally, little Charon. It's spelled Charon after the ferryman across the river Styx into the underworld of Pluto, but it's pronounced Charon after Charlene Christie, the wife of Jim Christie, who discovered Charon. And as we look at Charon, we see this dark area near the North Pole. This is an area we believe contains a lot of hydrocarbons that have been altered by sunlight to what we call compounds that are, there's some sort of reddish tint to them in real color, called tholins. And the other big feature here are the canyons. These canyons are quite deep, and you'll see landslides along their edges, and perhaps you'll see some features that look like they have flowed, maybe like glaciers or even like icy lavas. We would never imagine before this mission that we had a geologically active Pluto. Well, if we thought we didn't have a geologically active Pluto, no one could have imagined Charon. This is just an incredible world. Everything you're looking at is mostly water ice, but around some of the craters, we see ejecta of ammonia, giving us an indication of some of the materials that may be hidden beneath the ice. And so with that, I'm going to end our tour of the solar system this morning. We'll visit other places, other times, but I'm going to come back to you here for a moment, and then I'm going to open one more program here that we're going to take a quick look at just to finish up. And this is going to show us Earth. As that comes up here, let's see. Maybe that will come up quickly here. And again, I invite you, if you have any questions about our solar system at all, or about the geology of our own planet, you're welcome to put those in the comment section or a Facebook Live feed. Or if you are watching this in recorded version on YouTube, you're welcome to contact me through the community links there. And so let's see if we have this ready now. All right, so I think we're ready to tune in to our own Earth. And to do that, we're going to hop over here to Google Earth. And let's see if we can now navigate here to the southeastern US. And the reason I wanted to show you this is I wanted to show you where we're going to be talking about over the next few days. I've decided to turn this adventure into one of, we're going to basically look at impact craters between here and totality. So that's why we're calling it From Impacts to Totality. And we're going to come here into the Atlanta area. Of course, those of you in Charleston, you're over here. And we're going to come here to the area I call home. And let me get rid of the roads here. They're a little distracting in this. There we go. And so we're going to be trekking from the Atlanta area off to the west, headed out to the path of totality. But along the way, we're going to travel first to an area that my colleagues and me call we've called for a while the Manchester Woodbury impact structure. This is something that we discovered and been working on for almost 20 years now, getting very close to the final evidence that this really is from an asteroid impact long ago, about 800 million years ago. And this region, it's almost 200 kilometers long by about 70 to 80 kilometers across. We've lost some of the structure due to much more recent faulting around the time of the dinosaurs, 200 million years ago or so. But we're going to show you that, show you some of the highlights of this. And because it's so large, we have now, you're hearing this for the first time, renamed this the Roosevelt impact structure after the Roosevelt State Park and the area of Warm Springs where Franklin Delano Roosevelt had his little White House that he actually passed away at back in 1945. We're going to travel from there over to the confirmed impact structure called Wetumpka that is just north of Montgomery. Wetumpka was formed about 84 million years ago, and perhaps you could see the circular outline there. So we'll be showing you the Wetumpka impact structure. And then we're going to go to another likely impact structure in Mississippi. Did you know that there's an impact structure in Mississippi? So we're going to have to travel all the way across to Jackson and then turn north to an area called Kilmichael. And so we'll go to Kilmichael. Let's see, is that the... Yeah, so here we go. And out here in the woods, there's just a tiny expression of an impact structure. And let me see if I have my, may not have my database up here, but maybe I do. Let's see if I have the one that shows the exact location. Yeah, so we'll zoom in here, and you might notice just the edge of something that looks like a structure here. This is called the Kilmichael disturbance. We're going to attempt, I've never been there, so we're going to attempt to look at Kilmichael And then we're going to go south into Louisiana, into an area called Brushy Creek. This is an area that there's not a whole lot to look at here in this view, very vegetated area, but there is a small structure here. This maybe start to see a little bit of it right here. And the Brushy Creek, we have colleagues that have shown us good shock quartz from this region, and so there is the belief there really is a relatively young, maybe in the last couple of million years, that we have an impact structure that was created here. And then we're going to travel over into Texas to Marquette. Marquette is another. This is was like Wetumpka, created, we believe, during the time of dinosaurs. And the Marquette Dome is the central part of our impact structure, that's north of College Station, Texas. And then we're going to travel into College Station, where we will look at the badiocites, the ejecta from another impact structure that isn't in our field of view here, that is up in Virginia. The Chesapeake Bay impact about 35.5 million years ago sent material out across the southeast, including the tektites, the Georgia tektites here in my state, and also sent material over into East Texas. And we might have some luck finding some pieces of glass here in this area from that event. And we also have in this area, the Brazos River that cuts through the Cretaceous Paleogene boundary that has ejecta from Chicxulub that was hit here famously 66 million years ago to cause the demise of those dinosaurs I was mentioning. And then finally, we will be in well, I really had not thought about this, but we might also look at Bee Bluff along the way. We might as well. And then the path of totality is right through this area. And so we're headed somewhere in here. And hopefully the skies will be clear on Monday, and we'll be able to bring you some live coverage along with everybody else in the universe, seemingly, of the eclipse. And so thank you for being with me here, either live or recorded. And again, if you have any questions, please put your questions into the comments section of our Facebook Live feature, or send me messages through my YouTube channel if you're watching there. So with that, I'm going to come back to you and hope you have a wonderful remainder of your week. And we will be checking in with you from time to time in this journey from impacts to totality. Again, thank you very much, and see you a number of times the rest of the week, and hope you enjoy. Bye-bye.